right, we're up and running. So, do you have Travis, Sandhya, do you have any questions on the 5-1 assignment?
No.
No.
Okay, I want to try something a little different today. I'm going to use a video from a class we did in the spring. And so here, the point is, if you go to your website right here, and if you scroll down to lesson 5.2, you can see my cursor down there. I'm going to use that video number 3. So if something doesn't come through clearly, first of all, you can speak up. You can just talk over it and let me know something's not right. And I don't know how clear it's going to be. And then you can always come back here and just click on this link right here. Okay, lesson 5.2, number 3. That's the one I'm going to be doing. So the lesson today is on area. And we're going to do this video thing. Let's see how it goes. Okay, well, nice day out there. It sounds like some rain later, but wow, all of a sudden we have very nice spring weather. As you can tell, this was done in spring. So last time we did this reverse derivative process called antiderivatives, and you had a relatively short assignment. Are there any questions on the assignment? On any of the problems from lesson 5.1. Number 9, okay? So the 9 area was one of those where you had to rewrite, integrate, simplify. Okay. Morning, Jen.
Morning.
Yeah. So anyway, the question was asked about number 9 on the previous assignment. That's where we are. So if you look at the 7, 8, 9 section, we were supposed to, start with the given, rewrite it, integrate. So when we have number 9, we have the integral of 1 over x times the square root of x with respect to x. Does everybody, Richard, do you get what they did there? X to the negative 3/2. That means on the bottom you've got x to the 1 times x to the 1/2. So on the bottom you have an x to the 3/2, and you could write that as x to the negative 3/2. Well, then, pretty straightforward. Do your power rule. Up the power by 1, so it goes from negative 1/2 to negative 1/2, and then divide by that, that higher exponent of negative 1/2. Of course, that's the same as multiplying. Instead of dividing by 1/2, it's the same as multiplying by 2. So that's why the 2 is on the top, and it's still negative. Of course, we have to have the plus constant there. So, does that make sense, Richard? Yeah. Good. Other questions from last time that we should take some time at looking at? All right. The lesson is 5.2 and it's entitled Area. I told you that when you're doing an integral, one of the miracles is that if you can take the integral of any function, that'll give you the exact area under the curve. no matter how crazy shaped the curve is. So you zoom in on this a little bit, and we can look at the subheadings here. So we're going to use, you're going to be seeing today, we're going to be talking about sigma notation. Sigma notation. Sigma is a letter of the Greek alphabet, and it's in I don't know if you've had experience with that in statistics or any other course, but we'll be talking about that. Understanding the concept of area, approximating the area of a region, and finding the area of that region using limits. So limits play a role again today. So let's talk about sigma notation. So that thing that's circled there, that's sigma notation. That is, in the Greek language, capital sigma. Capital sigma, just like our letter S begins with the S sound, sigma, and it indicates sum, and that's the reason it begins with that sound, sum. So in other words, it just says add up everything. Now, to get more into, let's see, I'll blow that up even more. So when you look at this notation, you've got on the bottom I equals 1 and n on the top. So that means from 1 to n, add up a sub 1, a sub 2, a sub 3, all the way up to a sub n. So this just says start at 1, end at n, and do that for all the a sub, whichever, that's called the index. And so it says when I starts off at 1, add A1 to A2 to A3, all the way up to AN, and you can see that's the way it's written out. So it's just a notation for adding a bunch of things up. All right? So let's take a look at some examples of sigma notation. So the top one says, starting at 1 and going to 6, add up all the numbers. Okay, so the first time I is 1, second time I is 2, I is 3, all of it. So add up the first 6 numbers. Okay? And of course, that's just arithmetic. We could do that. Okay, just to show you again how math has different ways of doing things, look at part B. On part B, it says, starting at 0 and going to 5, add up all the numbers plus 1. So the first time through, I is 0, 0 plus 1 is 1. Just to keep track of where we are here. The second time through, I is 1, and 1 plus 1 is 2. Anyway, just keep going until I is 5, and 5 plus 1 is 6. And you notice we wind up with the same sum that we had up in part A. So a couple different ways. So the index can start at any, start at any number. So you always want to pay close attention to, obviously, or the whole problem doesn't make sense. Where are you starting and where are you ending? Part C. And by the way, for whatever reason, these little counters often begin with I, J, or K. That's not very important, but it's just kind of a common increment that is used for keeping track of these. So in part C, the counter J starts off at 3 and goes up to 7. All right, so the first time through, 3 squared. Second time, 4 squared, 5 squared, 6 squared, 7 squared. And of course, that would be 9 plus 16 plus 25 plus 36 plus 49, which of course we could calculate. Sometimes you're going to see this in fraction form, like you see in part D.
J starts off at 1 and ends at 5. So you got 1 over the square root of 1 plus 1 over the square root of 2 all the way up to 1 over the square root of 5. Let's go down to F. I wanted to show you an important concept there. So F, basically, let's see, how can I gotta see if I can show you an example. Yeah, so if we look over here, you can think of f of x being this red curve, okay? And what's the height of the curve at any point? F of x. All right, so in effect, and we could call the width of the rectangle delta x. So really, f is just the sum of all of those rectangles. All right, so when you come through the first time at point 1, what's the f of x1? Multiplied by delta x. Length times width, that'll give you the area of the first rectangle. And then the second rectangle, all the way up to the nth rectangle. Just again, the picture is that we're adding up these rectangle areas, and you can see that even though it's really rough, we've got approximately the area under the curve. Now, I want to show you what's going to happen here when we look at this animation. It depends a little bit on, so there's one rectangle underneath, and then there's 7. And as that gets bigger, you can see how when you add up all the rectangles, we're getting really close to the actual value below the blue curve. And in fact, if n approaches infinity, you're literally winding up with this, and we can do that by limits, and we're literally winding up with the area under the curve. So we're starting with this rather crude looking, rectangles, which don't match all the way up to the curve. But as you can take the limit as it approaches infinity, you can see, hey, we can actually get the area under that curve. So that's the concept we're looking at here. All right. So the next thing we want to look at is a little exploration here. Story goes like this. Carl Gauss is in probably an elementary classroom. His teacher's got a headache or something, and he doesn't want to deal with the kids right now, and he says to them, all right, quiet down. I want you to sit down, and on a piece of paper, I want you to add up the numbers 1 to 100. He thought, well, that'll take him a little while, give me a chance to have a little peace and quiet. And just about right away, Gauss has got his hand up saying, I got it, sir. And the teacher said, no, I wanted you to add up all the numbers from 1 to 100. He says, I have it, sir. So what Gauss did is he thought of it this way. He said, let's write all the numbers. He didn't write them all down, but 1 plus 2 plus 3, all the way up to 100 on one line. And down below it, let's write the same thing backwards. 100 plus 99 plus 98, all the way down to 1. Okay, now you're probably wondering, why did he do that? Well, look what happens when you add vertically. 1 plus 100, 101. 2 plus 99, 101. 3 plus 98, 101. All of them turn out to be 101. And so it's really 100 multiplied, multiply 101 times itself 100 times. Except for one thing, he's got 2 lists, and we only wanted 1. So then take 100 times 101 and divide by 2. And that's the answer he got, 5,050, which is correct. Okay, so what Gauss discovered there, just by thinking in a different way about how to do the problem, he discovered one of our theorems from today. And you can see it down there on the bottom. When you need to add up all the numbers from 1 to n, that's the same as taking n times n plus 1. You know, in the problem, n was 100. 100 times 1 more than that, 101, divided by 2. And you'll see later today, that's one of the that's one of our major theorems that we're going to take note of. By the way, Gauss, famous mathematician, and yesterday was his birthday. I know this sounds silly, but that's a big deal. Let me I lost my way here. Okay, here's Gauss, famous, he's the guy that discovered the normal distribution curve that you see here on the left, that famous bell curve, and he discovered many things. He's called the Prince of Mathematicians. This is a German banknote in his honor, and here's a postage stamp. Yesterday, Google, even their doodle was dedicated to him. I guess, I can't remember. We take a look here at the information page. Yeah, way down there on the bottom. Gauss would have been 241 years old yesterday. So that tells you how long. Anyway, he's, you see here, Prince of Mathematicians. Yeah. Pretty famous guy. From a mathematical point of view, very famous. Okay, so here are those theorems I was telling you about. The formulas will be very handy. You don't have to memorize these, but you want to keep these close. I would say put these in your notes. You'll see them in your book too. So here's the one. Here's the one we just saw. Gauss said, hey, if you want to add up all the numbers from 1 to a number, just take that number times itself plus 1 and divide by 2. Shortcut. Otherwise, you got 100 numbers you got to add up. Okay? Let's take a look at number 1. Number 1 is kind of a no-brainer. It says, hey, when you need to add up a constant from 1. So this is like saying, if you need to add up a constant n times, well, that's called multiplication, right? So if you need to add up 5 6 times, you add up 5 6s, that's 5 times 6 or 30. So number 1 isn't much of a revelation. I think we all knew that one. But now comes some tougher ones. Number 3, hey, what if you want to add up a bunch of squares? So this one, just look at the way it's labeled here. So that would mean, 1 to 10. Let's add up all the squares. So 1 squared plus 3 squared plus all the way up to 10 squared. Okay? Well, you can hammer it out the long way, or you can just take the number you're counting up to, 10, make that n, and take 10 times 11 times what? 21, because you have to double it and add 1, and then divide by 6. And that's a lot shorter than doing it the long way. And finally, number 4, if you want to add up a bunch of cubes, numbers can get really large. Here's the shortcut. What are you counting up to? Let's say it's 20. So then you would take 20 squared times 21 squared and divide by 4. So obviously there are many others, but these are the 4 that we will make use of. And it's just kind of nice. Again, don't memorize them, but keep them handy. They can make your work a lot shorter. All right, so let's take an example of a problem. And we want to show you how you can evaluate a sum, and you can, at the same time, make use of some algebra to simplify things. So here's our original problem up here. For I equals 1 to n, add up I plus 1 over n squared, and do it for n equals 10. Okay, 10, 100, 1,000, and 10,000. All right, so obviously we're not going to add up 10,000 add-ins. That would be an extremely excruciating problem, but by finding the algebraic answer to this, we can simply substitute in 10,000. So, taking a look at the problem right here, you notice what they did in the first step. They took this 1 over n squared and pulled it out. You know that in taking derivatives, we would often pull a constant out because it wasn't affected by the derivative. Well, guess what? The same thing is true in an integral, and the same thing is true in a sum. This 1 over n squared, n squared is whatever constant you're given, and 1 is a constant, and so you can pull that 1 over n squared out. What's remaining? The sum from 1 to n of I plus 1. Now, this is going to look silly, but that's really two sums. The sum of I from 1 to n plus the sum of 1 from 1 to n. The reason that's helpful is, you recognize this? That's that Gauss formula. Okay, if you want to add up all the numbers up here, let me just quickly go back and look. Yeah, it's that formula there. We also had it right here. It's at number 2. Okay. So now let's go back, blow this up a little bit again. So where did that n times n plus 1 over 2 come from? It came from that formula we just looked at. And what happens when you add up 1 n times? You get, 1 times n. 1 n times. 1 times n is n. And then, you see what, now this is algebra. How did they get from up here to here? They got a common denominator. So in order to add these two, you need to multiply this fraction by n over 2. And when you make it n over 2, then you can combine it with this n squared plus n.
It's when you make it 2n over 2. 2n over 2, yeah.
Combine those two and you get this. And now, let's multiply 1 over n squared times the entire fraction. So, you know what I mean? You can take n squared divided into n squared, and that gives you, let's see. Here, let me do it this way. So just to demonstrate what they did there, that's algebra, but they took 1 over n squared, and then they took an n out of the top. So this is another way to write that problem. And then, of course, that n cancels with this one down here. And you see how you wind up with n plus 3 on the top and 2n on the bottom. Okay. So all of that whole thing boiled down to, instead of something we have to add up n times, there it is. So for example, for n equals 10, 10 plus 3 is 13. 20 on the bottom, 13 twentieths. And here's 13 twentieths in decimal form. Plug in 100. 103 on the top, 200 on the bottom. Anyway, so without excruciating, so by doing the algebra ahead of time, we can make these sums fairly straightforward. And I don't know if you noticed, but they seem to be heading toward what? They're getting closer and closer to 0.5 to 1/2. So let's just take a look at this. Now, so another way to look at this is we take this n plus 3 over 2n that we just figured out a few minutes ago, this one, and we bring it down here and we say, all right, let's take the limit of that as n approaches infinity. So 10 to 100 to 1,000 to 10,000, we're heading obviously up to infinity. You remember how to do limits up to infinity for fractions? Sure. What's the degree on the top? What's the degree on the bottom? Oh, they're both, therefore, the limit will be the leading coefficients, 1 over 2. And does this appear to be approaching 1 over 2? It sure does. You see how that's getting closer to 0.5. So that's tying a little bit of our previous work together. This makes sense that this is heading toward a number, because we know how to take a limit like that. Okay. So, where this is all headed is you can take a bunch of we've got this curve, looks like a half a parabola aiming down here. It's actually negative x squared plus 5 is the equation. See it up there on the top, then up here. Okay. I'd like to find the area under that curve. So one way to doing it is dividing it up into some rectangles underneath. Now that's not perfect because you can see the rectangles fall short. And you get that excess pink area there. Well, okay, that's basically a summation, adding up the area of rectangle 1 and rectangle 2 and rectangle 3 and so forth, adding up all your rectangles, and you get a summation problem. And the height, that's this f of right here, and the width, as you can see, is 2/5. So length times width. And then do it for all 5 rectangles. Okay, well, that answer turns out to be 6.48. But you can see we're short. We're not high enough. You can also take the rectangles that go to the top, like you see in the picture on the bottom. And you can see that one's going to be too big. It's over the top. And sure enough, when we take those rectangles and add them up, we get 8.08. And the real answer is somewhere in between. Okay, well, the good news is, remember our little demonstration? That when you take the number of rectangles and increase them, look, it gets more and more accurate. In fact, the limit as the number of rectangles approaches infinity, you're going to get the perfect. And so here's the thing I'd really like to point out to you. Right here on the bottom. So what happens as you take all these rectangles and add them up as the width of the rectangle goes to 0? So you see how the triangles are getting, the rectangles are getting skinnier and skinnier as we move to the right. Delta x, that width, is getting smaller and smaller. And guess what you get? The final answer is, voila, the integral is the exact average of all of those. And so the integral really does give you the area under a curve. That's what this ends up at. So let's practice some sums. So let's do number 1. So how do we find the sum of 3i plus 2 from I equals 1 up to 6? Okay, so I'm going to write it out down here below. So the first time through, I is 1. 3 times 1 is 3, plus 2 is 5. Second time through, I is 2. 3 times 2 is 6, plus 2 is 8. Third time through, I is 3. 3 times 3 is 9, plus 2 is 11. You can see this is going up by 3 each time, right? So we got 3, 4, 5. So let's just do 6. 6 is 18, 10, 20. Okay, let's add those up. 13, 24, 38, 55, 75 is the answer. Okay, now I've got a really cool thing to share with you. And that is this part right here. It says use the summation capabilities of your graphing utility to verify your results. So guess what? Desmos does this really, really cool. It does summations. Here, let me just show you. Here's what we would do. You type in the letters SUM. And as soon as you put in the M of SUM or summation, right away you notice this thing popped up. Okay? Now, what were we supposed to do? We were doing I equals 1 to 6. Right? So let's go back. You can click in here and change the N to an I equals 1. And then up on top, put 6. Then the expression was what? 3i plus 2? 3i plus 2. And you notice right here is the answer, 75. So I encourage you to use Desmos to, like they said, verify, and 75 is what we got as our answer. Okay, let's do another one up here. Let's do number 4. Okay, number 4, we have, make this go a little higher. So on number 4, J starts off with 4 and it goes to 6. So basically we're going to be doing 3 over 4 plus 3 over 5 plus 3 over 6. That's it, from 4 to 6. We got it. Now let's add those together. Well, we need a common denominator. So what can I get from the lowest common denominator from 4, 5, 6? Well, 4 and 5, the LCD would be 20. And 20 goes into 60. It looks like 60 is going to be my common denominator. Okay? So 4 goes into 60. 15. I made that too long. Let me get rid of that. All right, so let's go for a common denominator of 60. So we've got 15 times 3. Sorry. So we get 60. 4 goes into 60 15 times. So multiply top and bottom of that first fraction by 15. 45 60ths. Next one. 5 goes into 60 12 times, so it'll be 36 60ths. And the last one would just be 30 60ths. Add them all up, and what do we get? 81, 101 60ths.
It should be 111 60ths, which I discover in a few minutes here.
Check that one out on Desmos.
So 81 plus 30 is 111.
And we're using the variable J, 4 to 6. So change that to a J. 4 to 6. And then for my expression, I need 3 over J. Okay, well, you get the decimal equivalent. Let's check that. 185. So if we go back here, 101, 101 divided by 60. Okay, I think we get the correct answer. Let's check that out.
The final answer should be 111.
Thank you. I added wrong. Thank you very much. So 45 plus 36 is 81. Yeah, 81 plus 31 is 111. Thank you. Okay. And now 111 divided by 60. Yep, and you can see it's the correct answer, 1.85. So anyway, very nice. Use Desmos as your verifier. All right. Let's see what's okay. So now here's this practice in getting used to this sigma notation. So how can I write number 7 using sigma notation? Okay. So we know we need the sigma notation. And it doesn't really matter what letter you use. But you can see this number in parentheses keeps what? Starts at 1 and goes up to 11. Okay, so now how can we write the expression? Over 5i. So 1 over 5 stays the same, but joining 5 on the bottom is this number 1, 2, 3. So you see that that would be a way to write that. How about number 8? All right, so we have sigma notation. Let's say J this time. And J starts off, it starts off at 1 and it looks like it goes to 14. And what do we have? 9 over 1 plus J. So you just got to look for what's repeating, what's always there, and then what's the part that gradually changes, and then from what to what. So that's practice in just trying to get used to this sigma notation. So that brings us up to the assignment. Now, you probably.
Yeah, I'm gonna go to the assignment because I cleaned it up a little bit. The assignment is for 5-2. We're just gonna work on 1 to 11 the odds. So how did the audio come through, and how did the video come through? I'm just interested in how that worked out.
It worked pretty well.
Oh, good. Did
Yeah, I thought it worked pretty well too.
Oh, good. Did you have any technical questions or anything about that you're wondering about? Have you guys ever used sigma notation before?
Yes.
Yes.
Okay, so both of you are familiar with that. All right. Well, if no, and interesting, I only had 2 of you here this morning. Thanks for your attendance, and I think we're going to close it off, and I will see you tomorrow.
See you.
Thank you.
Have a good day.
You too.
Bye.
Bye.